In the previous lecture, we discussed the limiting mass of white dwarfs, which we also call Chandrasekhar limit, and we have looked at the reason behind the Chandrasekhar limit and how the actual value of the Chandrasekhar limit depends on various physical processes. Now, the value of the Chandrasekhar limit is in the ballpark of about 1.5 times the mass of the sun. But if a compact star gathers more mass, then what happens? So, in this lecture what we will look at is what happens to a configuration if the mass grows beyond the Chandrasekhar limit. So, upon exhaustion of nuclear fuel, the core of a normal star undergoes gravitational collapse to form a compact star. This we have already discussed in the previous lecture. And we have also seen that the larger the mass of the star, the larger is the mass of the core. Now, for stellar masses above about 10 times the mass of the sun, that is as a normal star, if the star starts out with a mass larger than about 10 times the mass of the sun, the core nuclear burning is not halted by degeneracy and proceeds all the way to the iron peak elements, so producing iron, cobalt and nickel. The inert iron core, which has been produced where there is no nuclear fuel, now contracts and it is held by degeneracy pressure. But around the iron core, there is material which is now hot enough to burn and produce more iron. So, this shell burning keeps adding more and more iron to the core, and eventually the mass of the core will exceed the Chandrasekhar limit. What will be the fate of this object? So, this is now too heavy to find pressure support. A rapid gravitational collapse will ensue, and this will cause a quick heating and photodissociation of nuclei, followed by an electron capture. We will explain what we mean by electron capture shortly. But as a result, a very rapid gravitational collapse will occur, and it will generate a huge amount of gravitational binding energy, which will interact with the envelope of the star and will be accompanied by an explosion. So, let us take a little more detailed look at this. We know that in free space, if we have a neutron, free neutron, and we leave it in free space, in some time it will decay into a proton and an electron and an antineutrino. And this is because the combined energy, rest energy of the proton and the electron and the antineutrino is less than the rest energy of the neutron. So, the remaining energy difference can go into the kinetic energy of the products. Now, consider the situation that we have a very dense state where electrons have an energy which is not just the rest energy, but also the Fermi energy, and so is true for protons. Now, if the sum of these energies, the energy of the electron and energy of the proton in such a situation, if that happens to exceed the rest energy of a neutron, then the reaction would proceed the other way. The inverse beta decay will occur with a neutron and a neutrino as a product, while the protons and the electrons combine to do so. So, that means As you go to higher and higher densities where this becomes favorable, the number of electrons will just be captured by the corresponding number of protons and number of neutrons will get produced. As a result, as we proceed to higher and higher densities beyond what is available in white dwarfs, electron capture and neutronization becomes abundant. One can compute what are the ratios of the atomic number to mass number as a function of density. This is mass number by atomic number on the vertical axis and density on the horizontal axis. Typically, in a terrestrial nucleus, this value is around 2, but as you go to higher and higher densities, the equilibrium of this kind, which is called beta equilibrium, where the chemical potential of the neutron equals the sum of the chemical potential of the proton and the electron, leads to this ratio going to higher and higher values. As you go to very dense situations, this value increases dramatically. So, this is called neutronization or electron capture. This reduces the number of species of particles present, because you are combining electrons and protons to form neutrons. You create a neutrino, but usually that neutrino escapes from the system. So, as such electron capture proceeds, matter will become progressively neutron rich. Depletion of electrons will cause the degeneracy pressure which was supporting the white dwarf type configuration to disappear. So, it will rob the structure of the electron degeneracy pressure. As a result, density will rise rapidly until halted again at a very high density, where now the neutrons basically are in a situation where they are almost touching each other, and that will be near nuclear density. So, in matter now consisting mostly of neutrons, such a configuration is called a neutron star. These neutron stars also have upper mass limit, somewhere around 2.5 solar mass to 3 solar mass. So, exact value is not yet known, because the nature of the interaction between nucleons at such high density is still a matter of debate. However, if the collapsing core happens to have a mass which is even larger than this mass limit, then even the forces between neutrons and nucleons will not be able to stop the gravitational collapse, and a black hole will form directly. Now, these collapse processes are very quick, because the electron degeneracy pressure which was holding the starting configuration disappears in the process. It takes only a matter of seconds for a star to collapse from a degenerate iron core to form a neutron star. The energy released in this process causes a catastrophic explosion of the envelope, and these are known as explosions like supernovae or gamma ray bursts. A supernova is triggered by the collapse of a massive star, which causes an explosive ejection of stellar envelope, and a compact object is left behind at the center. Now, we are in this illustration, we are taking a journey to the core of the star. As you can see, different stages of nuclear burning are happening at different radii. This is one, further down one more shell, and the center is the iron core, which is going to collapse and release a lot of energy, which is going to throw out the envelope, creating a supernova. At the center, what remains is a neutron star, and many of these neutron stars are visible to us as pulsars. Again, that aspect of neutron stars we will discuss later in the series. So, a star's journey to a supernova can be illustrated in this diagram of progression of central density on the horizontal axis and central temperature on the vertical axis. In the lower left hand corner, you begin and go through hydrogen burning, then helium burning, then carbon, then oxygen, silicon, and go to iron. And at this point, you have produced an inert iron core, which will eventually go supernova. So, the central densities undergo a huge increase by many orders of magnitude. Supernova itself has a total energy that is released is in the region of about 10 to the power 53 ergs. Most of it is carried away by neutrinos. What remains in kinetic energy is about 10 to the power 51 ergs, and what comes out in radiation in the supernova explosion is about 10 to the power 49 ergs. If the stellar core happens to be very massive and a black hole is formed right away, and if such a core was spinning very rapidly, then some part of the envelope of the star stays behind, accretes into the black hole in a fast spinning accretion disk, and in the process jet like ejection of matter happens, and this jet formed bore through the expanding envelope and shoot out at relativistic speeds. If our line of sight happens to be in the cone of that jet, then you see a very bright flash of gamma rays. These are called gamma ray bursts. Neutrons, which are created in this due to electron capture, these neutrons, some of these neutrons also fly around at great speed, are absorbed at a rapid rate by the matter around, and transmutations occur, and eventually they undergo beta decay, and heavy elements beyond iron are generated this way. This is an example of a neutron star surrounded by the remnant of a supernova explosion. The central white spot signifies the radiation from a neutron star, and the matter around, seen in an X-ray image, shows the debris from the supernova explosion. So, these neutron stars that we are talking about are supported by neutron degeneracy pressure, and the interaction between the neutrons as well as neutrons and protons, which at very high density happens to be repulsive. So, the repulsive strong interaction and neutron degeneracy pressure act together to support neutron stars. To solve for the structure of such neutron stars, we have to use the Tolman-Oppenheimer-Volkoff equation. General relativity is absolutely essential in this case, and equation of state which describes the interaction between nucleons. Beta equilibrium has to be taken into account, and that tells us that the composition will be around 90% or so neutrons and about 10% or so protons and electrons. However, uncertainty in the knowledge of the nuclear equation of state, which is the nature of force between nucleons, leads to some uncertainty in the prediction of mass radius relation as well as in the prediction of limiting mass of neutron stars. Beyond the limiting mass, whatever it may be, if the mass of the configuration exceeds that, a black hole will result. So, in a neutron star like this, the internucleon distance is about 1 Fermi. So, that will immediately give you that the mass density is about 10 to the power 15 grams per cubic centimeter. With that, for mass of about a solar mass, the radius will turn out to be about 10 kilometers. So, these are the typical numbers for a neutron star. Neutron stars also spin very fast, spins in the range millisecond to minutes, and have strong magnetic fields, about 10 to the power of 8 to 10 to the power of 14 to 10 to the power of 15 Gauss, which have already been seen. Combination of these can give rise to rather exotic phenomena such as the pulsars as well as magnetars. This slide illustrates that the GR is essential for describing neutron star structure. So, if we take a single nuclear equation of state and plot the mass radius relation, mass on the vertical axis here and radius in the horizontal axis, computed from the full TOV equation including general relativity, you get this line which is seen in red. If instead we had used only the Newtonian approximation of the hydrostatic equilibrium equation, what we have got is this blue line. So, clearly that is completely out of reckoning for such highly dense objects, where general relativity plays a very important role. The importance of nuclear forces can also be seen if we compute the structure with full general relativity and with neutron degeneracy pressure alone, we get a maximum mass which is in the ballpark of 0.7 times the mass of the sun. On the other hand, we have started a configuration with a mass which exceeded 1.4 times the mass of the sun. So, clearly if neutron degeneracy pressure was the only pressure available to halt gravitational collapse at these densities, then no neutron star would exist, because the initial configuration itself would have exceeded this limit. So, the reason why the mass limit happens to be much higher than this is nuclear forces. So, nuclear forces, this is the potential as a function of internucleon distance, schematically plotted. At large distances, the potential is negative, that means the force is attractive, but when the nucleons are brought very close to each other, less than a Fermi or so, we sample this repulsive branch of the internucleon forces, and this repulsive nature which adds to the pressure that can oppose gravity, and hence neutron stars exist with masses of more than 1.4 times the mass of the sun. The range of masses that we have actually observed go up to about 2 solar masses in neutron stars today, but many more measurements will happen in the future. However, that is not sufficient to constrain the equations of state very well, because we have not been able to measure the mass radius relation of a neutron star very accurately yet. What is shown here in this diagram are the predicted mass radius relations from various different equations of state, which uses various assumed forms of the internuclear forces at high density. Clearly, some of these equations of state predict maximum mass below the maximum mass actually observed, and hence those equations of state can be ruled out, but there are many which rise above the known maximum mass. So, therefore, they will still survive. One of the key aspects of the study of neutron stars is to in fact constrain this. Various types of observations of neutron stars are being carried out and also are being planned for the future, which can pin down the mass radius relation of a neutron star well, and as a result can pick out which of these relations are correct, and therefore will tell us what is the form of the pressure as a function of density, and that means what is the nature of the internucleon forces at very high density. If directly a black hole is produced at stellar collapse, then as I mentioned, a gamma ray burst may be seen. The accreting matter onto the black hole from a disk spinning around the center creates these fast moving jets, and these jets then give us flash of gamma rays if we happen to be in the direct view of the jet. If we now want to take a census of these different types of compact objects, and let us say we look at a typical galaxy like ours, we have a total of about 10 to the power of 11 stars. The number of white dwarfs that have been produced over the history of our galaxy are about 10 to the power of 10. On the other hand, neutron stars are a much smaller number and even smaller number of black holes. We have been talking about the uncertainty in the equations of state of neutron stars. Let us discuss a little bit more detail about where this uncertainty comes from and possibly how we might mitigate it in the future. What are the basic features of a neutron star equation of state? We know that the matter is degenerate. So, Fermi energy is much larger than the temperature. So, therefore, the role of temperature is minimal. So, we do not need to consider the role of temperature in the equation of state. We also know that the matter is in beta equilibrium, which means this balance of chemical potentials persist. At very high density, the beta equilibrium entails that the proton fraction will go to about 1/8 or 12%. Now, nuclei get progressively neutron rich as density rises, and they coexist with free neutrons and then dissolve altogether. The equation of state at very high density is where the uncertainty lies. So, if you go through the interior of the neutron star, we find that baryons should be fully inside nuclei until a density of about 4.3 times 10 to the power of 11 grams per cubic centimeter. Beyond that, if you want to do further neutronization, then the nuclear structure becomes such that it cannot hold this extra neutron anymore, and neutrons begin to drop out of the nuclear structure and form a free background distribution on its own, a neutron sea. So, you have free neutrons and nuclei at this point. So, this phenomenon is called neutron drip. As you go to higher and higher density, the fraction of neutrons in the free neutron sea keeps becoming larger than the number of nucleons within the nuclei. Eventually, at about 2.4 times 10 to the power of 14 grams per cubic centimeter, which is the nuclear density. So, that is known density inside an atomic nucleus. At densities beyond that, all nuclei will dissolve, and you will get a free mixture of neutron, proton, electron plasma. Now, material below this density in a neutron star is called the crust, which is in the outer kilometer or so of the neutron star, and matter above this density is called the core. Now, as you go further and further into the core, the density will keep going higher to even beyond this, and beyond about 10 to the power of 15 grams per cubic centimeter, the nature of matter is really unknown, because the nature of force is unknown at that point. Neutrons form a sea with very high density. So, therefore, they are all very proximal. So, this state of neutrons, interior neutrons, actually ends up forming a superfluid, and the protons end up forming a superconductor, where the mediating attractive force is actually the strong interaction between them. a schematic illustration of the structure of a neutron star. Let us take about 1.4 times the mass of the Sun and use one of the equations of state from the literature. Then this is density, this is density in the vertical axis and radius in the horizontal axis. As you can see, the radius is about 11 kilometers here, and as you come from the surface of the star to the interior, there is a dramatic increase in density. You pass nuclear density at this point, and all of this is a mixture of free neutrons, protons and electrons. Nuclei exist in this outer region, which is the crust, where there are no free protons. Protons are all in the nuclei. Some neutrons are in the nuclei and some neutrons are free outside. And if you show this in a logarithmic fashion, you will find that you can clearly see the demarcation of these two regions. You have very outer part of the crust where everything is in nuclei, and then above 4.3 times 10 to the 11 grams per cc. There is a mixture of free neutrons and nuclei, and that is the inner crust region over here. So, the solid crust is about a kilometer thick and it forms in minutes after the birth of the neutron star. The mass of the crust is about 1/100th of the mass of the Sun. The rest of the mass is all in the core. If you look at the proton fraction as a function of baryon density, so as you get to denser and denser regions inside the neutron star, the proton fraction undergoes an increase, decrease and then increase all over again, going to a maximum of to 15-16%. That is in this specific equation of state. So, you have in the interior about more than 80% of neutrons and about 15% of protons forming a sea, and these neutrons form a superfluid and these protons form a superconductor. Illustration of these various layers are shown in this diagram. The outer blue part is the crust, the pink part in the interior is the outer core, where you have this neutron superfluid, proton superconductor and so on. The inner black part with question mark is the region where the equation of state is uncertain and the nature of matter there is still not fully clear. Now, to get a feel for why we have such trouble understanding nuclear equation of state for neutron stars, this diagram shows what we can actually check in the laboratory. In the laboratory, we can check low density matter or high density, high temperature matter, because when we try to create high density matter at using accelerators, we also produce this material at very high temperature. What our laboratory experiments cannot produce is this high density low temperature matter, which is in the lower right hand diagram. So, therefore, there is no direct laboratory measurement of the properties of the material that neutron stars are made of. We have to understand the properties of this neutron star material based on other measurements we make and extrapolating through theoretical means. And this is the main problem with trying to understand the equation of state of neutron stars. Terrestrial matter is that we are normally familiar with are at low density, and they are nearly symmetric, that is, the number of neutrons and number of protons are roughly similar. On the other hand, neutron star matter is at a very high density and they are also highly asymmetric. The number of neutrons are much larger than the number of protons. So, any interaction that depends on high power of density or high power of asymmetry would make it difficult to predict the behavior based on measurements at lower values of these parameters. Now, if you look at the total energy of the neutrons in MeV as a function of density, then you can see that up to 10 to the power of 14 grams per cubic centimeter is relatively low. And equation of state for such energy is actually well formulated at rho less than nuclear density. Now, at higher densities, the energy per neutron keeps rising, and as it keeps rising, typically above the rest mass of other possible particles like delta, sigma, lambda and so on, then at some point it may become favorable to produce those particles and have them in the mixture and not just neutrons and protons alone. Exactly what particles appear at what stage is again somewhat uncertain. You can have quark matter, you can have condensates. Many body interaction between these particles play a crucial role, and again understanding many body nuclear effects remain a challenge even today. So, additional particle species at high density may include hyperons, that is heavy baryons, lambda, sigma, delta, chi and so on. There could be mesons like pions, kaons. The kaons have strangeness, and if you have these mesons, because they are Bose particles, they are likely to form condensates. Or you could even have deconfined quarks. Phase transition to deconfined quarks may occur with the hybrid matter in between. And at sufficiently high density, a mixture of up down strange quark matter has been thought to be the matter ground state, and that ground state might be below the nuclear matter. And if you go through the barrier and able to reach this UDS matter ground state, then all matter which comes in contact with such a material may be converted to UDS quark matter. And if you form a star with such matter, they would be called quark stars, and it has been postulated that such stars may also exist. So, these are self bound configurations as opposed to neutron stars, which are bound by gravity and supported by nuclear forces. All of these deviations from pure nucleons tends to soften the equation of state. That means reduces the pressure compared to that of pure nuclear matter alone. So, if you happen to have, let us say, deconfined quark at high density, then its energy per baryon versus 1 over baryon density, if one plots that, then you might get a curve like this, which will represent the equation of state of that quark matter state, and this blue may represent the equation of state of nuclear matter at lower density. A common tangent between the two will indicate a phase transition. This is the standard Maxwell construction, where matter may undergo a first order phase transition being nuclear matter at densities up to this point, and then transit to quark matter and be quark matter at densities above this point. There will be no matter at densities in between this. So, there will be a density jump at the phase transition point. So, this is the first order phase transition. There are also other types of phase transitions, higher order phase transitions that have been postulated inside neutron stars. So, all of this is not directly verified so far by observations. If you do form quark matter inside neutron stars, the favorable state, energetically favorable state for this quark star at high density is what is called color flavor locked state, where you have specific color flavor combinations form Cooper pairs, for example, up red and down green and things like that. So, that would become the quark matter ground state at very high density, known as CFL over here. So, experimental or observational constraints on the equation of state come from laboratory constraints, which include measurements of nuclear binding energies, neutron skin thickness, dipole polarizability, giant dipole resonances. So, these are all measured in major nuclear physics facilities. Then we have astrophysical constraints from the masses and radii of neutron stars. how fast a neutron star can spin, that can also tell us something about the interior of the star. If you can find oscillations of a star, then that tells us something about the interior as well, or tidal deformabilities when two stars come close, and if you can deform a neutron star. For example, when two neutron stars merge and give rise to gravitational wave events, then the tidal deformability can be measured, and that will also tell us something about the equation of state of neutron stars. And there are general constraints on equation of state, such as causality, which is sound speed should not exceed the speed of light. Thermodynamic stability, that means energy density must be a positive definite and a monotonically increasing function of pressure. So, all these constraints can be imposed on the equations of state, and one can then try to isolate what are the allowed sets of equations of state given our current state of knowledge. Now, as we improve the constraints, as we bring in more constraints, we should be able to narrow down this range of available choices of equations of state. What we have today is this blue region in the pressure density diagram that is allowed by the constraints that we have. So, this blue region, if you then use the Tolman-Oppenheimer-Volkoff equation and produce neutron star structures, non-rotating neutron star structures, and produce mass radius relation, they would look like this. So, there is still a pretty large range which is allowed. On the other hand, there are equations of state which do predict mass radius relation outside these boundaries. So, if we now further measure masses and radii with greater accuracy and narrow down the region that is available within this mass radius plane, then that will put a much tighter constraint on the allowed range of equations of state, and this is what astrophysical measurements are trying to do at this moment. The neutron stars, apart from being very dense, having very strong surface gravity, also have very fast spin and fairly strong magnetic fields. Now, what is plotted here is a distribution of the known neutron star spin periods and known neutron star magnetic fields on the vertical axis. So, as one can see, the large number of neutron stars we know, which are primarily known to us in the form of radio pulsars, form a group here with a spin period of about 1 second and magnetic field of about 10 to the power of 12 Gauss. However, there are neutron stars which are known at other extremes. You can have a neutron star with a much faster spin period, nearly a millisecond spin period, with magnetic fields of the order of 10 to the power of 8 Gauss, or 4 orders of magnitude lower than this. So, these are all observed objects, so they have been found. Several neutron stars with very strong magnetic field have also been found. These are called magnetas. And some neutron stars have very long spin periods, thousands of seconds. So, they have also been found, but the large majority remains here. These different properties of neutron stars begin to affect each other. Because of magnetic field, there are torques on the neutron star, and those torques lead to spin down of the neutron star. If material falls on the neutron star from outside, the material interacts with the magnetic field of the neutron star, and if this material is bringing in any angular momentum, that can even increase the spin of the neutron star. Various physical processes associated with transport properties in the neutron star interior, its spin evolution, as well as accretion of matter on the surface, can all affect its magnetic field in the long run. So, the magnetic field of the neutron star also changes as a function of time. In the lecture that follows, we will discuss a few aspects of these behaviors of neutron stars.